Hello everybody, we're going to talk about Riemann sums and the definite integral and what the two have to do with one another. This discussion will be based mainly on a lot of definitions right here, although we want to make sure that we put some practical use to it as well. So let's get started with the first line of business. What is a Riemann sum? Well, we need to define a couple of things. First of all, we're going to let f be defined as a closed interval on a closed interval from A to B, and let delta be a partition of that interval from A to B. A partition, by the way, is the decomposition of a set into subsets whose union is the original set. So in other words, we're looking at separating our interval from A to B into subsets, into groups. We would think of these as the way we separated our rectangles here. Okay, so we've got this partition of A to B given by this interval from x0 being less than x1 being less than x2 all the way up to x of n being equal to b. And each delta x of I is the width of the ith subinterval in that group from x of I minus 1 to x of I. We say that if c of I is any point in that subinterval, that ith subinterval, then the sum from I equals 1 to n of f of c of I times each delta x, where c of I is between those two endpoints x of I minus 1 and x of I, this will be called the Riemann sum of f for the partition delta. Well, looking at our drawing here below, the illustration is really meant to show us where we're going to find that illustration. So if we were to pick one of these intervals here, let's call this one I. This is our ith rectangle, our ith partition, right? Ith partition right here, we say, well, in this sense, there's a variable c of I right here, and it is between x of I, so this is our third rectangle, and x of I minus 1, as we've discussed in our discussion of limits, right, in our discussion of setting up these subintervals, right? A couple of quick notes about these subintervals. First of all, you'll notice that the way this is drawn, each of these subintervals can have unequal widths. They don't have to be equally divided. The equal division that we used when we were talking about our subintervals was really just a matter of convenience. When we defined a left-hand limit or a right-hand limit and we drew rectangles, that was really more for our convenience than for any other reason. We can make those rectangles any other widths, but the point is that the largest of those widths, let's say if this was our drawing right here, the largest of those delta x's would have to go to 0, right? We want to make sure that that tends to 0 if we're going to set this up as a limit. So we want to set up a situation in which that's the case. The only restriction that we're talking about on what a Riemann sum does is that the Riemann sum is nothing more or less than a sum of all of those areas of those partitions in that partition, right? All the areas of those rectangles in that partition, right? And as long as there's no other restriction, as long as it goes from A to B, we're all set. Okay. So if we had been setting this up with our rectangles all along, rather than choosing a left-hand limit or a right-hand limit, we could have just chosen any point within our interval and said, well, okay, that will be our point x of I, and we'll try and figure out what's going to happen within that interval right here. That would be the point where we find our value of our function. So we're not going to be very specific. We're going to say fc of I represents the height of each of these rectangles at some point within each subinterval. Right? Now, again, we might want to define something and say, well, if we have rectangles that are all different values, right, we're going to say that the largest width, this largest width, is called the norm of x. And we write it this way, the norm delta right here. When we say this norm of delta, we're saying that, okay, in our partition, we take the largest, that's our largest subdivision. Okay, we want to make sure that largest subdivision has a way of going to 0 if we're going to do it using a Riemann sum. The other point that I want to make right here is that in our Riemann sum, other than just defining some point within each subinterval and letting that large subdivision go to 0, no matter how we divide it up, is that we can actually have negative values as a result of taking this kind of sum. So yeah, we can include negative and positive values as part of our Riemann sum. So that is an important point. And so we define our Riemann sum this way. We define our Riemann sum, as we said, on a partition, delta. And we say if f is defined on that interval from a to b, and we take the limit of those Riemann sums, of those partitions, as the norm. Remember, that's the largest subdivision, tends to 0 of our summation from I equals 1 to n of f of c sub I times each x, delta x of I, right? Remember, if these vary in width, this delta x of I could go to delta x for that particular subdivision. Right? If that limit actually exists, then f is said to be integrable on the interval from a to b, and that limit is denoted by, the limit as delta x goes from 1 to n of f c of I, delta x of I, is equal to what we call the definite integral on the interval from a to b of f of x dx. So what we're saying right here is that if we want r, we're going to take a definite integral, which we'll demonstrate here soon with the first fundamental theorem. But for right now, we define this animal, the definite integral from a to b of f of x dx, to be the result of taking our Riemann sum and allowing that limit, that partition, tend to 0. Okay, so we'll put some more meat on the bones of this particular theory here shortly in our next video.